Okay, so the topics for today are going to be, we're going to talk about joins, and then we're going to talk about insert, delete, and update. And we may or may not get to the start of subqueries. So if we do, we do, and if we don't, we don't. The big thing is joins, insert, delete, and update. And we started talking about joins last time. If you remember, a join is a way to combine the information from two or more different relations. So here I have a branch relation and a staff relation, and I want to know the address that Brad Vanderzanden works at. And if you look at the staff relation, you can see that it has a first name and a last name there, but it doesn't have any address field. And in order to find the address that I work at, you're going to have to use my branch number to index into the branch relation. And in the branch relation, you do see a city, a street, and a postcode. So I'm going to join the two relations using the branch number as the join attribute. And remember, what is branch number called? What do we call it? Foreign key. Very good. So here's the SQL query that accomplishes that join. So I'm doing my selection of attributes from the branch relation. And you see that I'm selecting now from two relations, the branch and the staff relation. And that should have been a lowercase b. So let me just quickly change this. There we go. So the B and the S are called aliases. They are short names that you can use in place of the relation name. So you see down here or up here, I just said b.street instead of saying branch.street. So I could have said branch.street, which would also be unambiguous. But by using these shorter alias names, it's just easier to write the where clauses. And it's a comma-separated list of relations that are involved in the join. And then the where, you can see that the first part of it is simply a Boolean, which is selecting for my last name and first name. And again, it's using s dot s dot. Now, I don't, strictly speaking, need to use the prefixes when the attribute names are unique to the relation. So in this case, because first name and last name can be found in the staff relation but not in the branch relation, strictly speaking, it's unambiguous which relation the attributes belong to. But then there's an AND clause that does the actual join, and now I have to for sure do the prefixing. So I say where the staff.branch number is equal to the branch.branch number. So what this first part of the where clause is going to do is return a tuple with my first and last name, but it's also going to return my branch number. And then it's going to, this AND is going to take that branch number, let's say it's B003, and it's going to select, using this equality, the tuple from the branch relation that has the value B003. And since now branch number belongs to both the staff and the branch relations, I can't use branch number without prefixing them with the name of the relation, because then it would be ambiguous. Okay? So this is a general example of the way a join query looks. Yes?
Is there an advantage of doing this sort of like an inner join? Or?
This is an inner join. We'll get to the definitions in a moment. You probably mean, is there any advantage? There's other ways to state this query, maybe.
Are they the same thing?
Yes.
Okay.
This is an inner, what you're seeing right here is an inner join.
So if we use the words inner join on our homework, is that fine?
That is fine. Yes. In fact, there's a preferable, we'll get to it, natural join is what you're really looking for. Okay? So this is a join operation. As you can see, it's simply this equality statement right here is the one that is in effect using the foreign key from the staff relation to index into the branch relation. And in the branch relation, branch number is the primary key. Okay, and we just talked about aliases, so we'll move on from that. And we'll move on. So you see, actually, in answer to your question, this is called an inner join. It's also often called a simple join. It's also called an equijoin. So I think I have that on the next slide. Yep. So when you use this equality operator to basically the equality, so a join is going to involve, let me actually write this down because it's important. So a join involves an equality comparison between a foreign key in one relation and a primary key in another relation. And that's a restricted form of a join. It's actually something called, so I'm going to put a little thing. This is often an equijoin. So there's more general join operations involving the inequality operators, but we're typically not concerned with joins involving inequality operators. Typically, we only care about joins involving the equality operator, and those are called equijoins. Okay, and an equijoin is also, will go by the name simple join or inner join. Okay, now there's some syntactic sugar you can use to simplify the query. So you don't have to use the equal sign. So in fact here we say from client C. So now we're selecting all the people who have left comments at properties, and we're selecting for their first and last name, the property number, and the comment. And now you see we use the syntactic sugar inner join. And when we say inner join, we have to specify the columns that the inner join is being performed on. And implicitly, it performs an equijoin on that column. So in this case, we're performing the equijoin on the client number. If the column names are different, you can't use the syntactic sugar. For example, in my student database that I created last week, I believe that in the student relation, the key is called ID, but in the student courses relation, the foreign key is called student ID. So I couldn't use the syntactic sugar there because the column names are different. That said, you try to choose the foreign key in general should have the same name as the primary key in the other relation. That's just good form. And when I first started, I didn't know that. So I'm telling you that generally your foreign keys should have the same name, but they won't always. We'll see an example of that. Well, actually, I can give you an example of that. Let's say we have a relation called staff. Okay, so we have a staff relation. Okay, and it has a staff number. And now we want to have the staff's manager. Okay, well, it turns out this is a foreign key. It's going to be the staff number for the manager. Obviously, we can't use staff number twice in the same relation, so we have to choose a different, in this case, more meaningful name for it, so we call the column manager. So this is an example where if I tried to find the name of this person's manager, I obviously couldn't use that inner join syntax because the column names are different. And in fact, it might look a little funny because the way I might write it is select, say, L name as, I'll say, manager from staff. And now I would actually have to say something like S1 because I'm going to use the staff a second time, S2. So I'm using it twice in the join. I might say where, say, S1 dot staff, we'll say last name equals Smith, and S1 dot staff number, S1 dot manager is equal to S2 dot staff number. In fact, we are selecting in this case S2's last name. That was ambiguous. So in this case, the relation is being joined with itself in order to find the manager's last name. So you can actually join a relation with itself, but in this case I would have to write out the equality for the join because the names of the columns on which I'm doing the join, which is in one case it is manager and in the other case it is staff number, those are two separate names. So I couldn't use the nice syntactic sugar anymore. So you really should become familiar with this equality way of expressing a join, even if for the most part you end up using the syntactic sugar. So questions about that? Okay. And then if you want to include all of the columns with the same name from both relations, you can do it even simpler. It's called a natural join. So here we're simply saying from client natural join viewing, and what that will do is find all the column names that are common to client and viewing, and it will perform the join on all such common columns. Now, that means they have to have the same domain type. If they don't, then you'd probably get an error message. So that's the simplest way to write it. And you can chain them. So I could say from client natural join viewing natural join something else. So you're allowed to chain them arbitrarily.
So it'll go through that, find like for all the column names that are the same, it'll match them up to that?
Yes.
And they have to be, okay.
Yes. Mm-hmm. I'll show you in a moment what it's actually kind of the theoretical thing that it's doing, how the long form of the algorithm. So let's see. Okay, so this is showing now that you can do a 3-table join. Before we were just doing a 2-table join. So here we want all the, let's see, for each branch we want the staff who manage properties and the city in which the branch is located and the properties they manage. So basically we want this result table. The the city, the staff member, and the property they're managing. And you can see, for example, that Ann Beach is showing up twice because she is managing two different properties, both of which are out of the Glasgow branch. So in this case, we are wanting to get the branch number on city from the branch relation, the staff number, first and last name from the staff relation, and the property number from the property relation. And you'll see we're only prefixing some of the attributes where there might be some ambiguity as to which relation they're from. And then you can see a comma-separated list of the three relations that we're using. And then in this case, there is no selection of a single tuple. It's just a straight join. So we join the branch number with the staff branch number, and then we join the staff number to the property staff. So this is saying, basically, find a branch number in the branch relation, any branch number, then index that into the staff relation. And this will get you several staff members because typically there's several staff per branch. And then this and says basically for each staff tuple we get, we're going to take that staff member's number and retrieve all tuples from the property relation that match that staff number. And then we finally order. You see there's a 3. The primary sort key is branch number. Secondary sort key is all staff within that branch. And finally, all properties managed by that staff. And you can see here that we could have actually done natural joins. So I could have more simply written this from branch B, natural join, staff, S, natural property P, and I could have gotten rid of the where clause. So that would work too. So I've just chained 3 of them together. And there should be no comma here. Okay? You got that? Because now I want you to do one. So let's see if I can make this bigger. Nope. Okay, so let me write down the find all courses taken by the mouses, return their scores, names, grades, and name of the courses they took. Okay, so let's go and take a look at so here's the student one from our database. Here's student courses. Okay, so first name, last name, ID, GPA. Here's the student courses. And there's courses. So the query I want is I want to find all the mouses. So in this case, if we say select star from student, you can see there's a bunch of mouses, Minnie Mouse, Mickey Mouse, Jerry Mouse. So what I want to know is for all the mouses, for each mouse, I want to know the courses they took, the scores they got in the course, and I want to know the name of the course. So you can see that course name, I want to know the first and last name of the student, and I want to know their scores in each of the courses. Okay, so what I want you to do is take a moment and try to write that query yourself before I go over it. So the query again that I want is I want to select the first and last names of all mouses, their scores, and the course and the names of the courses they have taken. So you're going to have to do a three-way join between those three, and here's the schema. So for student, it is first name, last name, ID, and GPA. For courses, it is course ID, course name, and location. And for student courses, it is student ID, course ID, grade, and score. Okay, so try to write that join query.
You said natural omits things. Do you mean everything that it has in common and omits it from the results, or?
No. I said that it uses all the common columns in the join.
Okay.
I didn't mean to use the word omit.
Okay, so when it won't return anything that isn't joined in all the columns. So if there's like an outline that doesn't have any relation to the other.
It won't appear. Correct. That's right. So, for example, if let's say there's a mouse here, and that mouse has not yet taken any courses or gotten a score for any course, it will not appear in the result. Yes.
So if you use like the primary key, just ID, the natural join would probably never work, right?
It won't work here because I didn't name the. You'll see that in courses and student courses, there's a common attribute called course ID, but I didn't do the same thing for student ID. So you're not going to. You may be able to use a natural join in part, but you won't be able to use it completely because there's not a common name for student ID.
Okay.
I'm just curious, how many still need a little more time? Don't be bashful. Okay, a few of you, so I'll let you have your time. Okay, so I'm just going to, I know you may not have finished, but at least you've thought about it, so hopefully the answer will help. Also, I will often do, I have the answer written down, but I'm actually going to try to do it from scratch because sometimes if you see me make a mistake, you can kind of, it may be helpful because you may also make that kind of mistake as well. So Dr. Plank says the same thing, that sometimes when he codes, he makes mistakes, but you still get to kind of see the kinds of mistakes he makes, and it might help you avoid them. So I want the first name and the last name of the mouses and their scores, which is right there. And I want the course name, which is right there. And you can see that there's no duplicates. First name, last name, score, and course name are unique across the three relations, so I don't need to prefix them with anything. Then I'm going to say from student S, courses C, and student courses SC, and that's just arbitrary. So I need all three relations in my query. And the first thing I'm going to do is I want to select any student whose last name is Mouse. Okay, so where last name equals Mouse. And notice again, I'm not prefixing L name because it's clear that it's from the student relation. But if you really wanted to make it clear, you could actually write s.lastname. Now I need to do a join, and that's going to be with student courses. Okay, so one of the art is knowing which relations you're going to join with. So you might think, well, how does Brad know I need to join with student courses rather than with courses? Well, one reason, the obvious reason, is there's no common attribute in student and courses. That is, there's no foreign key in courses that matches the primary key in student. Whereas if you look in student courses, you can see that student ID is a foreign key that matches the primary key in student. So there's a bit of an art to determining how to navigate your way through the database, and it has to be with matching foreign and primary keys. So in this case, I'm going to be locating all of the students' records. Another way to think of it is I'm going to locate all of the students' records from the student courses relation. So that will locate for each mouse. This statement right here will locate, this join right here will locate all of the course records for that particular mouse. And then we need to also locate the name of the course. Well, we have the course ID in student courses, but we don't have the course name. That's in courses, so we also then have to use the course ID to look up the appropriate tuple from the courses relation. Okay, so that should be the correct query. Of course, we always should try that out. So I'm going to copy it. I'm going to try to do it. And it didn't like, it says unknown column F name in the field list. So we can look back and, yep, in fact, that is wrong. It should have been first name and last name. And I have to fix the last name down here as well. But this time it seemingly worked. Minnie Mouse, score of 72 in fundamental algorithms. So all the records with Minnie, all the records with Mickey, all the records with Jerry. Okay, now you can experiment if you want. So I could do a natural join between courses and student courses, so we can see if this syntax works. Notice I have student here, comma, and now I'm forming a second relation by natural joining C with SC. And because of that, I should be able to get rid of this last one. So we'll see if that works or not. I actually just thought of it while I was writing out the query. So we'll see if that works. And of course, I have to fix first, last, last. So let's see if it's going to buy that. I could get the cursor right. And it bought it. So it was happy with me creating the second relation. So what I was doing here is creating a second relation that was a natural join between courses and student courses. So any questions about either of my solutions? Yes?
Did you go further? The student S and course C and interjoin them?
Could I do what?
Interjoin student S.
No, so I can't do an inner join. So I can't say inner join because there's no common column between S and this joined relation. But I could, but there's not a common column. So the problem is in student courses, the attribute, the column name is student ID. In student, the column name is ID. So I can't say inner join. What would, if I said, I can't say, so after I say inner join over here, and it gets complicated, I'd have to say over here, using a common column. But there's, if I say using student ID, that attribute doesn't exist in student.
Instead of using the on student dot ID equals.
I would have to check the syntax.
Okay.
Maybe. I might. I haven't checked. That's not syntax that I'm familiar with. So might work, might not. I'm fine if it works. It's just, it might be that you can say inner join on s dot ID equals sc dot student ID, but here, I don't think, I'll be brutally honest, I don't think this is going to work. We'll try it, and I'll get rid of this. I bet that something's wrong with this syntax. Ah, worked. Cool. So that worked as well. So in this case, instead of saying using, I use using if there's a single or if there's one or more common columns. Since the column names weren't the same, I had to say on. So now I haven't bought a lot, by the way. In fact, I have essentially just replaced the where clause with an on, and the inner join has replaced the comma. So it's not like I've gained a lot on that one. Yes. So inner join just says that I am going to join two relations and on a certain set of columns. Okay? It's no different. It's no different in this case than simply having, I could have just said gosh darn it. It's the same thing as saying that. So I'm not sure if your question is you're just not understanding quite what a join is, or inner join is just syntactic sugar. So the using part, let me go back to previous slide. So let me go back to this slide. So the using says if there is, I can use using when there's a column with the same name in both relations. So in this case, I was doing an inner join on the client and viewing relations, and they shared a common column called client number. Okay, but in the case where I was joining student with student courses, I gave different names to the primary key and the foreign key. So instead of using the using keyword, I had to say on, because the names of the two attributes weren't the same. So this is all just syntactic sugar for joins, okay? If we just say join, we mean inner join, okay? Again, it was meant to make it simpler for non-computer programmers to write these queries. The unfortunate thing is that when you have 5 different ways to write the same query, it can get confusing. And that may be what's confusing you right now. Lots of different syntax to remember. And I generally just remember one way to do it and do it that way. Okay? Pardon? You could in this case you're just using one column. If the primary key was 2 columns, then you would have to list both columns here. So you can list as many common columns as you want, but in general, the using clause is just going to include the keys or the attributes in the primary key, whatever that might be. Okay? And then this form right here, the natural join, that's even simpler to write because the natural join says as long as you want to include all of the common columns in your join, which is typically what you want to do, then you can just say natural join. You don't have to have this more verbose form. So all the joins that you're seeing, they're doing the same thing. It's just being accomplished with slightly different syntax. The end result is the same. Okay, just like that query that I did right now with the students, I wrote it 3 different ways and came up with the same result. If it's still unsure, you can come up afterwards and ask. I admit it's not the clearest. Yes,
so
Nish.
Can you use inner join without the using clause? And would it like function as the natural join?
No, if you use inner join, you're supposed to use either the using keyword or the on keyword. So when you say inner join, it's a promise. It's supposed to be a promise to the query optimizer that you will provide the column names. Natural join says I'm omitting the column names. Inner join says I will provide the column names. Okay. So the difference is natural join says I'm omitting the explicit equality and I'm omitting the column names. Inner join says I am probably going to try to omit the equality if I can and just provide the column names. Other questions? Yes.
So after you if you join two the ID from student and the student ID from student courses. So what's the name of the join column will be? I mean, you have two different names.
It will both, if I didn't provide this selection list up here and I had instead said select star, then both columns would appear in the result. You would actually see s.id as one of the columns, and you would see sc.studentid as a second column. So that's why you normally provide this more of a filter up here, because normally you don't want to see the same column duplicated in the result. So let me actually, okay, before I take further questions, let me show you what actually is happening with the join. Okay. So this is kind of the theory. It doesn't necessarily, the optimizer doesn't necessarily do it quite this way in practice. But in theory, what it's doing is the first thing is it takes a Cartesian product of all the tables in the from clause. So now it's duplicating the primary key columns and the foreign key columns. Okay, so you get a huge number of tuples at this point. And then you apply the where clause to reduce the number of tuples to just the ones you care about. So if you really did it in this way, you would get, if you had even small relations like, say, 10 tuples in the student relation, 100 tuples in the student courses relation, 20 tuples in the courses relation, you'd end up with 20,000 tuples that you would be narrowing down to the 9 that we got. Okay, so no query optimizer in its right mind actually does it this way because it's so inefficient. But theoretically, this is what is happening. So it's taking the Cartesian product, and when you take the Cartesian product, it would literally, you would see from the student one, you would have first name, which I'm going to abbreviate right now, last name, and ID. Then from the student courses, which I'm abbreviating SC, you would have student ID and score and grade. I'm running out of space and some other stuff. And so you would actually have every possible combination. So here you might have ID1 and ID2, ID1, 1, ID1, and 3. So when you do your join and you say s.id equals sc.studentid, it ends up only selecting this one tuple. The other tuples have mismatches between the ID and the student ID, so they'll be eliminated. Okay, so it then applies the where clause, which is typically the join, and then it, on step 3, it gets rid of the columns that are not in the select list. So at that point, it would be dropping, you would no longer have the ID or student ID or grade columns because those weren't requested. And then if distinct has been specified, it would eliminate any duplicate rows from the result table. There were no duplicates in this case. And then sometimes, I haven't gotten to it, there's a group by clause. I'll get to the group by. But the basic idea is that a join is a Cartesian product, and then you're using a where clause to narrow it down. So initially, you do have the same column represented in the, like here, ID and student ID. It's like you have both columns in that big joined relation, and then you're only selecting tuples where you have the same value in both columns. Yes?
So when you use your where clause,
Mm-hmm.
That's to narrow down the number of rows as much as possible.
Yes. Mm-hmm. So in fact, when I said in my query, when I said where s dot last name equal mouse, what a real query optimizer does is before it performs the Cartesian product, it actually applies any of these relational operators that it can to slim down some of the relations. So in this case, it would actually apply this predicate to the student relation, and that would narrow down the student relation to only 3 tuples. And then no sane query optimizer still does a complete Cartesian product. It would now do a more selective search in when it's doing this natural join. It'll find like course CS140, and it's only going to use the CS140 tuples from here. It's not going to try to actually take all possible combinations of values. But again, when they were forming the mathematical foundation for the relational calculus, which is what forms the basis for the SQL query manipulation language, this is how they defined it. So it just gives a formal definition, and then a query optimizer is free to implement it any way they choose fit, as long as the result is exactly identical to the result that would be obtained by running this algorithm. So it's like this algorithm is the gold standard. It's like you have to match the result that would be produced by this algorithm, but you're not constrained. The query optimizer is not constrained to use this algorithm. Okay. Other questions? Okay. So, in fact, you can also sometimes want to group. Okay, so in this case, let's say I want to find the number of properties handled by each staff member. So I don't want to list the properties. I just want to know how many properties each staff member is managing. Maybe I want to kind of gauge each staff member's productivity, or maybe I want to do some load balancing. So I just want to know the count. So in that case, what I want to do is group the properties by the branch number and the staff number. So I'm not even asking how many are being managed per branch. It's on a staff number basis. So I end up wanting to do a join between the staff and the property for rent. So again, I could do a natural join because the columns are the same. And once I have that, I'm going to be grouping by the branch number and the staff number. Now, I could just group by the staff number, and actually that would probably be a little more accurate, because even if a staff member works at 2 different branches, I probably want to know their total properties. What this is doing is saying if a staff member works at 2 different branches, then I'll get 2 different numbers for the staff member, one for each branch they work at. But this is the way the book chose to write it, so I wrote it this way as well. Okay. Now you'll see that in the group by, there's nothing that refers to the property number, yet what this count is actually counting is the number of property for rent tuples for each staff member, because when you're done with this join, for each property that the staff member manages, there's going to be 1 tuple in the result for that staff member. So then when we group by the staff number, it collects all the properties managed by the staff number into one group, and then it counts them. Okay. Now, Does anyone see a theoretical problem with this query? I will tell you that theoretically this query should be illegal. Anyone think back to restrictions we talked about last time on the grouping, on the aggregation operators? Can you remember there was a restriction about what attribute names could appear in the select clause? Only the ones that were in the group by clause could appear in the select. But you'll notice that first name and last name show up in the selection list even though they're not here in the group by clause. So that seems to be a violation of the SQL query, or of the rules, and yet if you run this query, it will work. Okay, and the reason for that, we haven't gotten to something called subqueries yet, but an intelligent query processor is actually going to break this query into one that initially only selects the branch number, the staff number, and the count star. So basically what it's going to do, let me get this, and let me copy this into here. And let me get rid of all of what I already have. Okay, so what it's going to do is it's actually going to first create an intermediate result. Okay, that's just looks like that. And I'm just going to, for the moment, put this in an intermediate result. So I'll say intermediate, and it doesn't actually, it creates a view, but I can't quite write it like this, but it's doing this. And then it's in effect saying select first name, last name, s dot branch number, s dot staff number, and staff count from intermediate and staff s. See, this now becomes intermediate. Now becomes intermediate. Where intermediate dot staff number equals s dot staff number. So what the query optimizer is able to do is break the query into two, and the intermediate query doesn't violate the rules because it only has attributes from the group by clause and the select clause, so it puts it into what's called a view, and then it's able to join the view with the original staff relation in order to get the outcome we want. So it turns out the query optimizer can do some fancy footwork to avoid the issue. So even though the query looks illegal, the optimizer is able to transform the query into two legal queries. Because I remember when I first saw it thinking, wait a minute, that shouldn't work. So I tried it and it did work. And it's like, how can that work? And then I figured out how the query optimizer could make it work. Okay, so questions. This is a join that involves grouping, which is very handy. Okay? So now a few definitions. So we call the inner join what we've just been looking at. So the inner join says that you if you have a tuple in relation 1 and a tuple in relation 2, then they only appear in the result if they match in the join. So if a tuple in one relation doesn't match a tuple in another relation, it's not included in the result. So as a result, example of that, let's say, go back to here. So notice I have Mickey Mouse, and I have Minnie Mouse, and I have Jerry Mouse. Let's say I insert into student values, and I'll put, this is another good mouse, Dorothy Mouse. ID 11, GPA, Dorothy Mouse is pretty smart, give her 4.0. So now, if I do my previous query, so now if I look, Dorothy Mouse is there, but if I do a join, Dorothy Mouse isn't in the result because Dorothy Mouse doesn't match anything, any records in student courses. So she's out of the result. So we call that an inner join because she is in the student relation, but she's not matched in the student courses relation. So that's an inner join. An outer join retains rows that do not satisfy the join conditions. So if we did an outer join, then Dorothy would appear, and you would see null for score and null for course name to make it clear that Dorothy Mouse did not match anything in the student courses relation. Okay, so when we talk about outer joins, there's three types of outer joins: a left join, a right join, and a full join. We don't actually say left outer join, but implicit in left join is the word outer. Implicit in the word full join is the word outer. Implicit in the word join by itself is the word inner. So if we just say join, we actually mean inner join. If we say left, right, or full join, we actually mean outer join. So a left join will include all rows from the left relation in the result, and any unmatched row in the left relation will have nulls in the columns from the right relation. So that's what I was just talking about with Dorothy. Dorothy wasn't matching anything from the student courses, had no records there, so Dorothy Mouse would appear, but she would have nulls for score and course name. Okay, right join, same thing, except now it's all rows from the right relation appear. So let's say that we added a new course to the catalog, CS465, but no one is registered for it yet. So when we did the right join, then you would see nulls for the first name, last name, and score, because there's no values for that relation in the other two, but you would see the course name, databases, and scripting languages in the fourth column. And then the full join, you're including all unmatched rows from both the left and the right relations. Okay, and there is syntax in MySQL and SQL for doing that. So if you want to do a left join, so actually let's do that right now. Let's just show you. I'm going to change this query now so that it becomes a left join. So instead of doing an inner join, I'm going to do a left join. And you see Dorothy Mouse showed up with two nulls. Okay, I'm going to try to do a right join and see if that does anything for me. It should, because there are some courses that presumably none of the mouses have taken. Nope, doesn't look that way. It looks like the mouses, that didn't do anything for me. Either they've taken all the courses or, oh, I know what happened. Just a second. Right join. Courses, natural join, student courses. I'd have to look at that. I think there's courses in there. Let's just look at student courses for a moment. Yeah, there's some like CS for non-majors. So I'd have to look more carefully, see why the right join isn't producing a course name called CS for non-majors. But let's just, let's see if anyone, let's select star from student courses. There we go, student courses SC, right join, courses C on SC dot course ID equals C dot course ID and see what that does for us. It looks like, wait a minute. Let's do just course C dot course name, and we'll do SC dot score and SC dot student ID. See if we get any nulls in here. Nope. Oh, that's because yeah, CS for non-majors. Okay, let's do an insert. Insert into courses, values. Let's see, what's a good one? Databases. Databases. I need the course ID first. I hate that. I got kicked out of the database completely. Okay. Insert into courses, values, CS465, databases, Mingal 524. Now we'll do our right join again. There we go. And databases shows up with no, because there was nothing for databases. So you can say left join, you can say right join, and you can say full join. So questions about that. So you have inner join, outer join has left, right, full. Okay. Questions about joins. Okay, in that case we move on quickly. There are 3 set operations that are supported in SQL. So you can take the union of 2 sets, you can take the intersection of 2 relations, and you can take the set difference of 2 relations. And I assume you know what I mean by each of those 3 operations. MySQL only supports set union. It does not support intersection or set difference. And if you're going to take a set operation onto relations, they have to be union compatible, which means that the two relations must have exactly the same number of columns, and each pair of columns must be drawn from the same domain. It turns out you don't have to have each column with the same name, but pairwise they have to have the same domain type. And that means if you start out with one relation having 4 columns and the other relation having 3 columns, you actually have to project the first relation down to 3 columns in order to make it work. So same number of columns and same data types. So as an example, let's say we have staff, professors, students, and administrators at a university. And as you might imagine, there might be some overlap. So some staff might be students, some administrators might be professors, some professors might be students. So here we find all our employees. So we select, notice how we first make them union compatible by selecting only the name from each of the 3 relations. So we first make them union compatible, and using the union keyword, we get all employees. And the union operator will eliminate common names. So it returns only unique. Every tuple in the result will be unique. This gives us all professors who are also administrators, but this operation is not supported in MySQL. I will show you next week how you can still get that intersect operation. It's actually from a join. And this is the set difference, so all administrators who are not professors. Sometimes you'll see minus as the keyword rather than except. Again, this operation, whether it's minus or except, is not supported in our version of MySQL. And we will do the modification statements on Thursday. So on Thursday, we'll do the modification statements, we'll do subqueries, and we will do some of the data definition language.